a more or less regular tetrahedron. At all times in our talking, my thinking out loud, we will remember that we are now aware of Heisenberg's indeterminism. We are aware of the fact that men, in making the most careful measurements, when we get down to the most minute phenomena, have been able to handle that the increment of measurement is so minute in relation to motions of electrons. So we simply have some very comfortable approximations. So this is an approximately regular tetrahedron. By regular you mean that it is what we call equilateral within approximate satisfaction. And something we're going to think about tetrahedron right away, some qualities about it that are worthwhile. First place, if I were to have some other kind of piece of geometry, a cube or octahedron, what's different between these? Well, let's assume that this tetrahedron is of cheese, making it very easy for me to cut it. If I were to take a sharp knife and cut the cheese parallel to this face here, cut down like that, I simply get a smaller tetrahedron. It is still a regular tetrahedron, it's just smaller. The only change is smaller. I would then cut parallel to one of the other faces, this face here. It's smaller still, but it still is regular. I cut parallel to this face. It's smaller still, but it's still regular. And I try the fourth face, and it's still regular. That is, reducing arbitrarily one side instead of all sides, a symmetrical time, seemingly an asymmetrical reduction, because I'm only cutting down on one side of the four faces, does not in any way violate the symmetry of the tetrahedron. Let me take any other piece of geometry, the octahedron, which is symmetrical. I'm going to slice parallel to one of its faces. When I do, what I get here is a little short leg. I find a hexagonal face here suddenly. And I don't have hexagonal face over here, triangular face. It is no longer symmetrical. It is no longer regular. I try it with a cheese cube. And what I have left is no longer symmetrical. This is a shorter leg here, and that's a long leg. So that we find by some experiment that the tetrahedron is the only, its center of gravity will have to move to accommodate the fact that one is being asymmetrically altered. So the center of gravity is going to move away from this face and out towards this face. So the center of gravity will form a little curve as it moves. In effect, the effect of my pushing in on one side and pulling out on the other simply makes the tetrahedron stay the same size and it seemingly moves. Motion could be a consequence of something that looks like this thing as a whole unit, all by itself. That's moving from here to there could be literally my pushing in on one side and pulling out on the other. If it were made of enormous numbers of little closely nested spheres, such as this tetrahedron over here, then if I took off one layer of very tiny little spheres and added on another layer of very tiny spheres, such as they were the size of atoms, and this is the way atoms themselves do pack, then all you and I would see was the tetrahedron moving. We'd see the great big mass of all of them. If I were to push in on a third face, I have this couple. I'm continually pushing in this spot and adding to this one, and we discovered, incidentally, the tetrahedron always had six edges, 4 faces, 4 vertexes, and 6 edges. And the 6 edges represent the relationships, the 6 relationships between the 4 stars, which are at the vertexes. And when we begin to try to make a tetrahedron by taking tubes, for instance, like this, or as the Indian would try to make a teepee, we find that these tubes won't go through a point at the same time. One of my own empirical axioms that I began to see that seemed to be operative in nature was that you cannot have 2 actions through the same point at the same time. And therefore, I said that whereas all the geometers had thought of their lines going through points, and even the non-Euclidean geometers, such as Whittaker himself of the last century, but to get into crystallography and get into making various kinds of crystals that are known to man, the crystallographers make experiments with tetrahedronal and octahedronal and cubical wire frames. Being idealized, a surface was not just a line continuum, it was a plane continuum, a plane that had no thickness and yet was a plane. It was a membrane, an infinitely thin membrane that absolutely divided the areas on either side of it, the volumes on either side. And when they theoretically constructed a sphere of a surface equidistant, I can make a triangular base pattern like that, all right. Now, if I try to put one in here, it doesn't fill the space, and it leaves a space that is not regular tetrahedron. A regular tetrahedron won't fit down into there, and this becomes very annoying. So that if you've seen that the priests were using 30-degree angles, 60-degree angles, you wouldn't see any way in which you could go ahead and develop mensuration of space from such a device. So you just throw it out, say it's a very pretty thing, and that's all about it. And the tetrahedron gets really left out. There was another basic way in which and a scribe for scribing a line and dividers for dividing a line. So they put up that point to start off with a scribe, then they put up the straight edge here and they draw a line through it. So then they take the dividers and they put it on the point and go over here. So they put the dividers over here and cuts through here, but it comes back to the same hole before. So then they try it over here. It simply cuts back through here. And all they can do is to stay on the line here, keep cutting through, and they don't get off the line. It's to be a very uninteresting kind of a game. And the line was infinite to them. Went on in a flat earth wherever the plane was infinite. So they wanted to play a game in which they, starting with a point, and they're sticking to it, and they strike here, and this time it makes a circle like that, a bigger circle, and from the same time, with the dividers over the same amount, they strike, and suddenly they get them 2 points where these circles cross off the line. Now it's nice and interesting. They said because the dividers were open to a known new angle, this was a known distance, and therefore this point was equidistant from these 2 points, and so it was down here. Then they dropped a line from here to the line. They call that perpendicular, and that was the beginning of their 90-degreeness. Essence of 90-degreenness, it begins here. There's another thing they tried to do, which was, so we see how they found the 90-degree angle. And they said it two parts would make 180 degrees, because that's the way it's constructed. They could prove that. Let's take our point again and run our line through it. Let's take our dividers, and they're opened up this distance, so I strike a circle around here. So they said, all right, now I come out to this point here, and my dividers are open this distance, so I strike here, and I can strike here. I go to this end of the line, and I can strike here, and I can strike here. So I can connect up. This is radius here, and this is radius by actual construction. This is the radius of the opening of these dividers, and this is 2, and this is also 2. Then they found that their dividers seemed to go from here to here, and seemed to go from here to here, but they didn't know that it was true. That was a coincidence, and they never could take any, and they could not use this in their game. They said, even though it seemed to be fitted by it, we can't say that our dividers really divide the circle into 6 equal components. they never were even able to deal with the rationality of six subdivisions of a circle. And so they dropped that all out, and up to this day, the Euclidean geometry in its most updated effect cannot prove this to be true. Starting our game the way you and I have started it, which we started with the whole of the universe, we started not with a plane geometry or a solid geometry. We started with an omnidirectional geometry. We started with totality of the universe and found out what the first geometry was. We found that we could also define something like a sphere as a plurality of points, possibly equal to this in all directions. I'm going to start then with a sphere. It's just one of the ways in which I can subdivide the total universe. That is a whole lot of stars, approximately equal to this in all directions from where I am as an observer. Now, then, that has a given radius. Now, I'm looking at the outside of that sphere, which is a whole so many stars that it looks superficially solid, if you want. I'm going to take a point on the surface of the sphere, any point on the surface of the sphere. I have my dividers open to start off with to draw the sphere. The opening of the point is the radius of the sphere. So I come to the surface of the sphere and I strike another circle here on the surface of it, which is then the same radius as that of the sphere. Here is the center of the sphere right here, so I can take any point on that sphere. I know this is radius out to this point, and I know this. I can just go to any point over here, and that's radius distance also. Now, with my divider still fixed at the same angle as with which I constructed the sphere, I'm going to strike another. I'm going to strike over here from this point, which I'll be able to do, cutting that circle on the surface. Now I know the distance over here to here. I know this point must be the same too, because it's on that circle, and I know these 2 points are on the surface sphere, therefore they're interconnected, and suddenly tetrahedron shows up again. I can also go to any other point on this circle outside of this chord. I know by practical inspection that this circle is very much greater than an increment of 1 chord. So I take any point over here I want, and then I'll take another point on the circle over here, again by radius. So this distance is radius. And then we know this distance from here to here. That's radius. And then we know the distance from the center of the sphere to it, and center to center of the sphere. That gives me 2 tetrahedra with a common edge. So there's 2 tetrahedra with a common edge. All of those lines are constructed without prime radius. There are planes going through those points through the center of the system. Those would be great circle planes. So here, then, would be, and the Greeks defined a triangle as an area bound by a closed line of 3 edges and 3 vertices. So there it was. The yellow triangle, this area bound by the 3 edges. But you and I know, starting with totality of universe, and then separating the universe into a thinkable set, into a local system, where we divide between the insideness and the outsideness. That now, supposing it is a sphere, the sphere as a surface is a unitary surface. It's a whole lot of little stars, which is true. But it is unitary, it has an external superficial externality, a convex side. We know that when we take a sphere and we draw a closed line on a sphere, let me just take one little one. Now going rhombic, and the diamond shape is called a rhombus. And there are 12 such faces. I put a diamond to a diamond. I need you to help me if you just stand over here and hold 2 of these together like that to start off with. Then another one will fit in here. Sometimes very reverse. Now, notice you've got this base, and hold yours up, and you'll find that it will. He's a hexagonal shape that fits right in. You can't help going the other way. Now we're beginning to fill all space and add on some more here. Okay. And yours. Now there's another shape to fill in. So a square, look at the square aspect and it'll drop right in. That is the square. You just put it on top, then I'll shake it. Wrong. Sorry. One of the interesting things, if you put these in a box and shake them, they will fit themselves into one another. It's quite a different kind of a fitting from taking cubes and get to really great accuracy. So I can make a bigger tetrahedron out of a little tetrahedron, but I have a space that I've left inside it. So is there any way that I can find out what it is? Well, there are 4 corners to this big tetrahedron. There's a little tetrahedron on each of the 4 corners. On each of the corners I can see 3 of the faces of the tetrahedron. There's a 4th face on the inside. Each one of the tetrahedron then has 4 interior triangular faces. Then I see 4 open triangular windows on each of the 4 faces of the big tetrahedron. Therefore, the thing that's in there has 8 equilateral triangular faces, and it's the octahedron. So we take this off and we try it, and we find, sure enough, it's so. It will fall in, incidentally, like that. It is self-centering. And so we find that we have then 4 little tetrahedron plus 1 octahedron make a big tetrahedron. Well, we have a Auricon 1. This has a volume of 1. This has a volume of 1. This has a volume of 1. I take 4 times 1 equals 4. I subtract it from 8, leaves 4. Therefore, the octahedron must have a volume of 4. Okay? Anybody didn't follow on that, though? Very interesting then. Now I have a rational value between tetrahedron and octahedron. If the volume of the tetrahedron is 1, the volume of the octahedron is 4. Quite interesting now. This is my first mensuration. This is my first arithmetical. That's it. Now we have a half octahedron here. And make another half octahedron like that, and I put it on this face. Each one of these, there are 4 of these to a half octahedron. Each one of these is a 1/8 octahedron. And we can see the central angles of the octahedron, which are the 90-degree angles. Take the 2 green ones and put them together. They make a half octahedron. And let's just face that off to this one, so that we'll really... So there is our octahedron, and we'll find that it will fit right up to our friend tetrahedron. I'm now going to put another one on another face of the tetrahedron. I'm going to put another one on this face. And there's one more face left. We'll put this on here, and what we have is a cube. So now there's something very interesting, because a cube has appeared, and it consists of 4 1/8 octahedra. Each one has a volume of a half. 4 times a half equals 2. Tetrahedron had a volume of 1, so 2 plus 1 equals 3. The volume of the cube is 3. Now this is pretty interesting, because we have a geometry suddenly coming up here where rational values that come out for tetrahedron, octahedron, and cube are all rational to one another, which they were not in the terms of the edge of the cube being unity and the 90-degree angle. In the terms of the 60-degree angle being used, we find that the system is turning out to be rational. Furthermore, we discover that inasmuch as the cube equals 3 tetrahedron, if we're using an accounting system of subdividing universe into its expected part and making an accounting of the universe, then the tetrahedron is an equal distance outside here, and that will be the resultant of forces. When these 2 things come together, they will make up a force that will run over here. And things that interested me about parallelogram of forces was that it was a neat mathematical way of making predictions, and you could do so. Explode, exactly contained by equal forces that hold them together. You say, I don't quite see that. I'm going to count that. Count how many vertexes there are here. 1, 2, 3. 3 in the southern hemisphere, and 6 around the crater, making 12. There are 12 vertexes here. Therefore, there'll be 12 radii leading to these points. You say, let's count the outer edges. And I discovered that the outer edges are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 9 makes 24. There are 24 edges and only 12 radii. So you say the edges, the tendency to hold the thing together, the circumferential vectors are twice the number of the radii. That is not true, because what is happening here is that I take this radius and this radius, I put 2 radii together, so that what you have here in this form, incidentally, is really quite exciting. Let me open these edges out smoothly. This one plus the space between it will fill up this space. I've made some models which we can see that going on. Now, those 6 parts, I'll take another 4 sets of these. Now, find the whole tetrahedron is divided then into 24 of these units. That unit is an interesting unit. When I want to make it up, I can make it up out of this triangle. This folds back in itself and fills in. Makes this unit. It's an interesting kind of a game that this could be made out of such a triangle, because the angle here is not 90 degrees. You can look at it, say maybe I think it ought to be 90 degrees, but you actually do the trigonometry, you find it's not 90 degrees. It's a very odd triangle. It's just a triangle which does fold up and makes that. If you want to make a regular tetrahedron, you can do so by taking a triangle. You didn't fold that out of one triangle, right outside of the bed. In fact, this is an extraordinary freak. This is the only triangle I've been able to find that can be folded into that same angle. This here is always about that same angle. It begins to form, to make that's a perfect pattern in here. Come back to its starting point. See, I understand it. And like that, come back to the starting point. Energy will go around and around and around inside a triangle, bouncing. And any triangle will hold an energy, just bouncing around and around and around, because you simply have a composition, any shaped triangle, bisect its edges, and you get similar triangles, and these angles will show up. So the ability to hold energy, a quarter tetrahedron and a quarter tetrahedron, see those together, and then another one here. They give a triangular base. I know that this new 1/8 octahedron is going to be twice the altitude of this one. I put this one at, it'll certainly be twice the altitude of this one. I'm making up a new 1/4 tetrahedron, and one like this, but twice its size. You know that this big one is going to have twice the altitude that these had, and we know this thing has twice that altitude, so we just drop it in here. We know it fills that space. Now I've got to find something that fits in here, into these spaces. And I put them back in the same spaces a different way, and so we try this. There they are in exactly the same space, but now this time they are arranged radially, and the time before they were arranged in layers. When they're arranged in this condition, the gray gets out to the outer edge of the big 1/4 tetrahedron. The energy relationships are fundamental. You know that in terms of centers of gravity, relative proximities, in this condition is much more cohesive. This one is tending to radiate, and this tending to collect. I was very excited when I began to discover then that the A's and B's appeared. Another one of these on here. notice that they form a plateau. They form a diamond and has a plateau. I put another one on here and forms the same plateau. And I put another one on here. Now I get diamond faces, and because there are 12 edges of the octahedron, and that 12 of these diamonds formed on those 12 edges, we simply get the rhombic dodeca. That is, you get the unit that's twice the size. Rhombic dodeca is constructed of the octahedron with the central angles of the tetrahedron extroverted on its surface. And the octahedron had a volume of 4, and these are each of them a quarter. There are 8 faces, so 8 times a quarter is 2. So I've added 2 to 4, and the rhombic dodecahedron has a volume of 6. In the same hierarchy that the tetrahedron 1, cube 3, octahedron 4, rhombic dodecahedron 6. So again, we find this is one of those major. If these legs are rubber, I can push on this vertex here. If these legs are rubber, and somebody pops and comes in this one. It's very easy to make that model by simply making a steel triangle and take 3 rubber bands to the center here and pull them, and it gets looking like this, and then pump your hand through, and you see the tetrahedron this way and then this way. So that you can make it turn inside out. Octahedron, you can't do that. Take octahedron, and supposing I push one of its vertexes, these are rubber legs. The most it can do is for those legs for it to turn in like this. One side nests inside the other, but it's not inside out. It simply is collapsed. If I try it with the icosahedron, all this will do is simply to dimple in. Tetrahedron is the only one in which if you push one vertex, and I do that on each of the faces, and I can cut through. So the same condition that I got in making the 24 little A's out of the regular big tetrahedron. Remember the 24 little ones out of taking each of the 4 pyramids on the 4 faces to the center of gravity of the system, and cutting each of those triangular pyramids into its 6ness by, I can do that to each of these faces here, and I'll give me 24 components of this unit, and they will all be 24 different components. But because they are formed on the center of gravities of the system itself, each of the 4 faces, because of the center of gravity, each of the 4 little pyramids formed on it, which look quite different from each other. The one on this side here, this kind of a base, the one on this side, this one, each one looks different. But each one has the same volume because it was formed. There is room for 20 around that point. Because there's 20, then I can take 8 to the 4th, which is 2 to the 4th power, gives me 16. And then I can have 2 times 2, which is 2 to the, I can have 2 to the 4th power plus 2 to the 2nd power equals 20. I can have 4-dimensionality is permitted in axiom is modelable. Then I'm going to have anything take place at all. I'm going to have 6 moves. I can allow the 6 moves. Every time I play this game of chess, we get 6 moves. That's the minimum. So I could go bing, 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 bing. Makes a kind of a figure 8. You keep going around like that every time there's a move. That is a really very frequent one. You'll find in what they call the vicissitude figures, this figure 8. Now I could make another one. I could go bing, bing. I might go like that. I might go like that. I'd land one point away from where I started, like that. I might go bang, bang. Thank you for that. Or I could go starting here, 1, 2, 3, 4, 5, 6. I discovered then that at the end of the 6th investable, a little over 5 minutes.